Hey friends, it's good to be back with you. Today I'd like to start talking about Fourier transforms and Fourier series, and we'll move on to Laplace transforms. Now I mentioned in an earlier video, there's a whole class of functions called integral transforms, and they all have the same sort of form. And these are the two that you're going to use by far the most, are the Fourier transforms and Laplace transforms. Now there are others out there, and they're well documented. If you want to go explore, I encourage you to do that. What you'll find out is once you understand one kind of transforms, the other ones come a lot easier. Now, the Fourier transform is a little different in the sense that there is a Fourier series and a Fourier transform. The series leads up to the transform, and since people will talk about Fourier series, I'm going to start there. That's what we're going to do in this video. Then we'll move on to Fourier transforms in a follow-on, and then we'll go to Laplace transforms. So that's going to be the next couple of videos that you'll see here. So what is this? Where did it come from? Well, Jean-Baptiste Joseph Fourier lived in the late 1700s and early 1800s. And his first job, actually, was to accompany Napoleon to Egypt, where I guess he seemed to be wanting to kill people that season. And when Napoleon bailed out and abandoned his army there, one of the people who got left there was Fourier. And he finally made his way back to France. But because of this experience, Fourier's earliest published works were actually about Egypt, the history of Egypt and some of the things he'd seen there. He moved on to mathematics and other things, actually later after the Egypt experience. You could do that back then. What got him to the Fourier transforms and Fourier series, now he didn't call it that name came later, was he was working on heat transfer problems. And he was able to write down differential equations that he then couldn't solve. There wasn't any obvious way to do it, and numerical methods were far in the future. So what he was doing was he said, if I use an infinite series approximation to the solution, I can make it as precise as I need to. Well, that infinite series is what we now call the Fourier series. So the big idea with Fourier series is that they're a way to approximate periodic functions. What's a periodic function? Well, a periodic function is something that repeats itself, and like a sine wave is the periodic function you know about. The periodic function you see a lot when people are talking about Fourier series is like a step function or box rectangular function, sawtooth waves, things like that. So let's take one that goes from 0 to 1 for a second, then goes to 0 again until 2 seconds, and just keeps doing this forever and ever. Okay? All right, that's a really simple periodic function. Where would you ever see this? Oh, I don't know. Does that look like a digital signal to you? Yeah, you'll see this absolutely all the time. So it's, there's a reason we would want to approximate something like this. Now, this is just one of an infinitude of periodic functions. So what Fourier was trying to do is, well, it's hard to write this down in a closed form way. Let's do this as a series. Fourier series can be expressed in two different ways. One of them is in a trigonometric form with a bunch of sines and cosines in it, and the other one is a complex exponential. Now, this is a short enough class. I don't really have time to go through all the derivations, and my guess is you probably don't need it. So let's start with the trigonometric series. Let me see. I'm going to write it right here. I'm going to leave this up there. I'm going to write it down for you. So the Fourier series in time looks like this. There. Wow. Now, it's the infinite series. I only wrote the first couple of terms. Doesn't matter how many terms I'm going to write. There's always one more. But this is enough to see the pattern here. So there's A's and B's are coefficients. These are just numbers. And what you can see here is there's an A1 times cosine omega t, B1 sine omega t, A2 cosine 2 omega t, B2 sine 2 omega t. So here's what it really, in a more compact form, this is what it looks like. Okay, that's a more compact form. Now this A0 term, that's basically a DC offset there. Notice there's no sinusoidal part of that. So the first thing we need to know is, what's omega? Well, if this is a periodic signal in time, it's got a frequency, right? Well, how long is the period? In this signal, that's the period, and then in this case it equals 2 seconds. In this particular case, it could be different for different signals. Before I get going any further, what's a signal? I just about failed controls in undergraduate school, and I just about did it again in graduate school because I couldn't figure out what a signal was. All right, a signal is just a voltage that means something, right? If I look at the power cable that's going into my computer over there, there's a voltage going through there, but it doesn't mean anything. There's no information encoded in it. It's just the sine wave that delivers power to my computer. What about, how about this wire right here? It's coming out of this microphone, and there's this little transmitter on my belt. Right here, it's going to the wireless receiver on the camera. What about the voltage going through that wire? Well, that really does mean something. What you're listening to is my voice that went through this wire. So there's information actually encoded in what's going through this wire, even though there's no information encoded in the power line going to my computer. So a signal is a voltage that means something. What's coming through this microphone, I've got clipped here and going into here, that's a signal. If you're flying an airplane and you're doing fly-by-wire, which all modern airplanes use, when you're moving the stick or the throttle or the rudder pedals or whatever, there's an electrical signal going to the flight control computer. Okay, that's a signal. That's a voltage that means something. All right, the DC power bus that runs the plane, delivers power to the various instruments and stuff. It's a voltage, but there's nothing encoded in it. There's no meaning to it. It's just power. That's all it's there for. So the difference between just power and a signal is whether there's information encoded in it. And so we're going to say that this is a signal. This must mean something, right? If this is the timing signal for a computer or for some digital electronics box, this actually means something. This is something we care about. So signal is a very, very important thing here. So what we're trying to do is we're trying to approximate this signal using this. So let's see, if frequency, I should make that, I'm going to make this a capital F. Sorry, guys. To distinguish from frequency right here, capital F and little f are two different things. So in the frequency in hertz, let's do this, hertz, which is in cycles per second, is just 1 over t. All right. If it takes 2 seconds for this signal to repeat itself, well, its frequency is 1/2 hertz. Well, cosines and sines don't operate on hertz. They operate on radians per second. So omega, which is the frequency in radians per second, is just 2 pi over t. It's not a very good pi. Here we go. All right. That's all that is. And remember, this is for periodic functions. We'll go to what's called aperiodic functions, functions that don't repeat themselves. That's where the Fourier transform is applied. But for right now, this is a Fourier series, and we're looking at periodic functions. So this is one way to do this. Now, the hitch here is I need to know omega. Well, I got that. This is going to be a function of t, so we're good to go there. What about these constants? Where do those come from? Well, those are simple to figure out using an integral. And I'm running out of room here. I'm going to erase some of this stuff. I'm going to leave this here, and I'm going to clean that up for us. All right, so AN is, make sure I get this right here, 2 over t. Let me write this out, and then I'll explain what all this is. Okay, that was a lot to write out, but here we are. So A of n, that's A0, A1, A2, all the way up, is just this, where this is the original function. This is the thing you're trying to approximate. And I'm sorry, I know I used F earlier for frequency, and I'm changing this on you, but this is how you see it in all the textbooks, so I want to use the standard notation. Omega we already got. N is going to be, whichever n you want. There's the n right there. And we're going to integrate through time. Now, T0 appears right there, and there's capital T. That's the period. All that's required is you have to integrate through one complete period, and it doesn't matter where you start. Now, with our square wave, probably we want to start at time 0 and go to time 2. Right? It would make the most sense. And it's going to be 2 different integrals. We'll break it down. But you notice the f of t for that between t equals 1 second and t equals 2 seconds? It's 0. So we really only have to integrate this, for this example, we only have to integrate from 0 to 1 second. And it's the same over here. That's the period again. There's the period. And we're just doing a slightly different integral. So that's all there is to this. If you want to create an approximation of that square wave, we can just plug that in here, or any other periodic function you want. Now, it's easy to imagine that pushing a bunch of sines and cosines around, as long as you don't have to do too much of it, it's okay. But boy, it's going to get complicated, and it's going to get complicated fast. All you have to do is start taking derivatives or something, and this just becomes way too much work, way too much work. Now, there's got to be a way to fix this, isn't there? There is. One of the things I wrote earlier, wow, I got to get a new pen, is there's this thing called the Euler relation, e to the I omega t. This is after Leonhard Euler, who discovered this. Okay, he was able to write a relationship between a complex exponential and sines and cosines. Well, that's sines and cosines, isn't it? Stands to reason there's probably a way to write this out instead of sines and cosines, which are comfortable because these are all real numbers here. If we're willing to live with complex numbers, it's going to get a lot simpler. And the electrical engineering world absolutely lives and dies on complex numbers. Anytime in the mechanical world you're dealing with anything that vibrates, acoustics, vibrations, anything like that, you're in the world of complex numbers. So complex Fourier series and complex Fourier transforms are absolutely everywhere. Okay, you can see I had to change pens. That blue one wasn't making it. But here's what the complex version of the Fourier series looks like. So we've got the A and B have been replaced by a single complex constant C sub n, and it looks kind of the same. Now I've written it out as minus t over 2 to plus t over 2, because that's what you always see in the books. But the same deal goes. As long as you integrate across one complete period, it doesn't really matter where the period starts. So if you want to go from 0 to t or whatever, it'll still work fine. And you can see there's the complex exponential right there. So when you try to develop the time domain Fourier series approximation, the summation goes from minus infinity to plus infinity. Now the reason is that in order to go from here to here, there's a bunch of basically bookkeeping and kind of algebra. If you're willing to live with a negative index, this is all it is. If you insist that these be positive, it gets more complex, or more involved, I shouldn't say complex. So in principle, of course, you're never going to go from minus infinity to plus infinity. That's impossible. So these are always truncated. They have to be. So let's say you're going from minus 5 to plus 5. Okay, n equals 5, minus 5 to plus 5, and just C of n is going to have a negative index. Well, that means that is going to be a negative number. It means that's going to be a negative number. Works just fine. So don't let the mechanics of this fake you out. Okay, this is all pretty abstract. Let's try to make this more concrete by grinding out some numbers on my computer, and let's see what Fourier series approximations look like. Now, I'd like to do this in 2 steps. The first of which is we're going to go to MathCAD, which is kind of like a math spreadsheet. It doesn't have anything to do with CAD. I don't know why they picked that name. And it's easy to read, though. That's the point. So I can show you the solution there. You'll be able to follow it easily, I hope. And then from there, once we know what we're doing, we'll go over to MATLAB, which is a more formal and more powerful programming language.